Okay, so this course, if we've been able to see the syllabus, you'd see the competencies for the course. Starts out with some basic arithmetic, and it is some relatively basic concepts that we start out with. But we cover them for a couple of reasons. One is some people have either been away from school for a while or have struggled with some of the concepts, and it's nice to make sure everybody is on the same page. Two, I tend to describe things a little bit different way than some people do. Rather than just telling you how to do stuff, I like to try to make sure you understand why. And the big reason for that is the third reason we go back over this stuff. When you get into the upper level topics like algebra and things like that, we've found through the years that one of the main reasons people struggle with it is they don't really understand what we're doing and why we're doing it with most basic stuff. So we're going to step back and look at some of those basics. One of the big basic topics we're going to look at today is going to be one of our simplest, but also one of the most misunderstood. And that is the concept of what is a number. If I were to put a 4 up here, how many of you would tell me that that's a number? Most of you would. Of course, some of you are sitting there thinking, oh, well, something's got to be up or he wouldn't be asking, right? 4 is an amount. It's what we call a numeral. To truly be a number, it has to tell us what it is. Not just how much, but of what. So we might have 4 cows. Now that's a complete number, telling us not only how much, the 4, which I'm going to refer to as the count, but also of what. In this case, cows, which we're going to call the name. Now, I'm not putting this out there because I'm going to be really strict about labeling stuff. Now, in the medical fields, there is a certain amount of things you do have to label. You should label milliliters versus microliters and milligrams versus micrograms and stuff like that. So we do have to make sure we have those measurements labeled. But if the answer is 7 patients and you just put down 7, I'm not going to be picky about having a label on something like that. But the main purpose I'm showing you this is because those labels, that name plays a very big role in how our numbers interact with each other in our math operations. So let's take a quick look at our 2 most basic math operations and how numbers interact in them. So look at addition and multiplication. Now you might be thinking, where'd subtraction go? And where's division, by the way? Well, addition and subtraction are the same operation. Just one's in forward, one's in reverse. So any rules or any conditions we put out there for addition also apply to subtraction. And of course the same goes then for multiplication and division. So anyway, in addition, let's do an example. Let's say we have 4 inches plus 7 inches. What do we get? 11 inches. Good. Let's look at what happened with our count and our name. So for the counts, we have 4 and 7, which becomes 11. We combine the counts. Let's look at the names. We have inches and inches, which becomes inches. We just keep the same name. Now, that may not seem like a big deal, but when we look at multiplication, there is a noticeable difference. If I have 4 inches times 7 inches, what do we get? It's going to be 28 inches squared. Perfect. When we're multiplying 2 lengths, generally we're looking at an area, so it's going to become a unit squared. So let's look again at our count and our name. We'll start out with our counts. 4 and 7 become 28. So once again, we combine the counts. We're multiplying this time, so we combine them with multiplication. The difference comes in the names. We had inches and inches, and it became square inches. So when we multiply, we also combine the names. That doesn't seem like much of a difference, but it actually is huge. That little difference there between addition where we just keep the same name, and multiplication where we also combine the names, defines how we do our processes of addition and multiplication in all of our different forms of numbers. Not only that, but it also limits what we can use in certain operations. For example, let's take a look at, let's say if we have 7 cows and 2 boys. Can we add those to get 9 cowboys? Doesn't work, does it? What if we switch it around? 2 boys and 7 cows. We get 9 boy cows. Anybody with a farm background in here? A couple of you. You'd be able to tell me that this is a whole bunch of, well, I don't know, long way to go for a joke. But there's a point behind the joke. I'm a math teacher, by the way, which means I'm required by law to have a really stupid sense of humor. You'll get used to it. You know, there is a point behind that joke. When we add numbers, since we're going to keep the same name, it implies that we must start with the same name. We cannot add cows to boys because they don't have the same name. Which one are we going to keep if there's 2 different ones? We don't know. So we cannot add those. On a little bit more serious note, we might have a measurement like 5 feet plus 2 pounds. What are we going to get? Well, trick question. 5 feet and 2 pounds. They have different names, feet and pounds, so we cannot combine those with addition or with subtraction. But if we were multiplying 5 feet times 2 pounds, when we multiply, we combine the counts, so 5 times 2 would be 10. And we also combine the names. Feet times pounds are foot-pounds. It's a unit of torque. Or if you're in construction and engineering, it's a unit of moment. When we multiply, we don't need the same name because we're going to combine the names. Now again, you might be looking at it thinking, okay, maybe sort of interesting, but why do I care? Because when we look at our other forms of numbers, it defines how we do things with those. Let's look at everybody's favorite form of number, a fraction. I heard some grunts out there. I'll admit, if I asked people on their way in the door what they hated most about math, I'd say 4 out of 5 would say fractions. Most of the others would say the teacher. Let's review. What's the top number? What's the top number called? Numerator. Very good. What's the bottom number called? Denominator. Well, let's look at the meaning of those words. The numerator. Every 10 years, our government sends out people to numerate the population. They are counting. Denominator. Well, we have different denominations of money, different denominations of organizations. To denominate means to classify or to give a name. So a fraction, the numerator and denominator, are nothing more than a count and a name. A lot of people look at a fraction and they see 2 different numbers. It's not. It's one number with 2 parts. Just like having 3 inches or 3 cows, we have 3 sevenths. So that 7 is a label, just like the cows or inches or pounds or anything else. So when we go to add fractions, 3 sevenths plus 2 sevenths, for example. Well, let's go back to 3rd grade or so. When you first being taught how to add fractions, that 3rd grade teacher told us to add fractions, you must have common denominators. So we do. Again, that was nothing new to fractions. Anytime we add numbers, we must have the same name. So having that common denominator is just having the same name. Then, once you had the common denominator, how were we told to add them? Well, combine the counts. Add the numerators. 3 plus 2 is 5. And keep that common denominator, right? Again, nothing special for fractions, and it's not just because your teacher said so. It's when we add any number, we combine the counts, then we just keep the same name. If I have something like 1/3 plus 2/5, can I add those the way they're written? No, they have different names. Later on, in a few minutes, we're going to see how to change their names, to change the denominators to make them the same so that we can add them. But for right now, all we need to know is different names we can't add or subtract them. On the other side over here, though, if we're multiplying 3/7 times 2/7, how are we taught to multiply fractions? Multiply straight across, right? 3 times 2 is 6. 7 times 7 is 49. Again, that's not a special process for fractions. When we multiply any numbers, we combine the counts and then also combine the names. If we had our 1/3 and 2/5, oops, not plus, multiply. Do we have to have common denominators? No, because when we multiply, we do not need to have the same name. We're just going to combine the counts. 1 times 2 is 2, and also combine the names. 3 times 5 is 15. Let's look at decimals. 0.21. Now, the formal way of pronouncing that would be 21 hundredths. Good. If I were going to add decimals, let's say 0.21 plus 0.3. Can I do it like that? Is that going to work? What's wrong? Decimal points aren't lined up. Why do we have to line up the decimal points? Because the third grade teacher said so, right? Well, if we look at this, this is 21 hundredths. This is 3 tenths. They have different names. Fortunately, I can just do this. If I add a 0, now that is 30 hundredths. And now when I go to add them, the decimal points automatically line up. 21 and 30 make 51. Where's my decimal point go? We drop it straight down. Why do we drop it straight down? Because when we add numbers, we keep the same name. 21 hundredths plus 30 hundredths has to be 51 hundredths. When we multiply, do I have to line up my decimal point? Say no. No. Okay. Because when we multiply, we don't have to have the same name. So I can go ahead and set it up like this. 21 times 3 is 63. Where does my decimal point go? Add a 0 and put it right there. Why? Because you were taught you have to count 1, 2, 3 decimal places in the problem. So you have to put 1, 2, 3 decimal places in the answer, right? But why? Third grade teacher said so. Well, this is 21 hundredths. We put a lot of faith in that third grade teacher, didn't we? This is 3 tenths. When we multiply, we do combine the counts. 21 times 3 is 63. But we also combine the names. Hundredths times tenths is thousandths. When we're counting up those decimal places and making sure we get that many decimal places in the answer, all we are doing is making sure that we also combine the names. We can even look at algebraic numbers. I know some people start to cringe when we throw letters in there, but it's really no different. Just like any other number, we have a count and we have a name. If I have 7x plus 15x, I'm going to get, just like any other number, I'm going to combine the counts. 7 plus 15 is 22, and I'm going to keep the same name, x. What if I have 5x plus 2y? What do I get? 5x plus 2y. Just like up here, 5 feet and 2 pounds could not be combined with addition because they have different names. 5x and 2y have different names. We cannot combine them with addition. We won't be able to combine them with subtraction either. On the other side, if I am multiplying 7x times 15x. I'm going to combine the count. 7 times 15 is 105. But I'm also going to combine the names. Just like inches times inches became inches squared, x times x becomes x squared. How about my 5x times 2y? Do I have to have the same name? No. I'm going to combine the counts. 5 times 2 is 10. And then just like feet times pounds became foot pounds, x times y becomes xy. Not so bad? So the question becomes, how does this tie in with the stuff we do every day? We might be looking at this thinking, okay, it's sort of interesting, but that's not... Where's all these labels? Where's all these names at when we're looking at our other numbers? Well, the concept that ties it together is another one of those very simple, but also very important and misunderstood concepts called place value. Now, I'm not going to insult your intelligence by deriving all the place values and all that stuff, but we're just going to throw them out here pretty quick. Starting at the decimal point, or at the end of the number, and working our way back. What's this last place value here called? Ones, then tens, and hundreds. In fact, those are the only 3 place values. That makes up what we would call our base group. Then we would have our thousands group. And within the thousands group, we have the same 3 place values, ones, tens, and hundreds. And then the millions group, ones, tens, and hundreds. And to name a place value, we name not only its place value, but its group. So this is just the tens place. Well, this is the 10,000s place. And this would have been the 10 millions place, and so on. And like I said, I'm not going to insult you by going through how to name numbers and all that stuff. But there are a couple of things about the place values I do want to point out. One of them would be something like this. If I were asked to round to the nearest thousand. Well, most of us know how to do that. What would that come out to be? 44,000. Good. But let's look at what it really means to round to the nearest thousand. Like so many other things in math, it comes back to a number line. And when we're being asked to round to the nearest thousand, what it's asking us to do is look at the number line and focus only on the thousands. Like 42,000, 43,000, pretend these are equally spaced, 44,000, 45,000, and so on. And once we focus on those, we look at the number 43,758, which is right there. And we ask, which one is it physically nearest to? Well, it's nearest to the 44,000. So that's why it's 44,000 is what it rounds to. Now, obviously, we don't want to have to draw out a number line every time we round numbers. So we have a shortcut. When we're asked to round to the nearest thousand, of course, the first thing we do is we find the thousands digit, which is the 3. And we look at that digit and the stuff before it. What that is telling us is that this is between 43 and 44,000. It is the next digit that tells us which one we're closest to. Since that's a 7, well, we know 5 would be right in the middle. 6, 7, 8, and 9 would all be closer to the next one up, the 44. If that digit were 1, 2, 3, and 4, it'd be closer to the next one down, the 43. This one's 7, so it goes up. Now, the only time that there'd be a problem there is if it were a 5. What would happen if it were a 5? Okay, perfect. Let me throw an example. Let's say this is 43,512. And again, still to the nearest thousand. Since 5 is in the middle, we're a little hung up. But we have been told always round it up. Do you know why we always round it up? Because this stuff over here. It isn't exactly halfway. That 12 actually puts it slightly past halfway. So even though that digit is a 5, and 5 would be right between, usually there's something after it means that we are closer to the next one up. The only way it would ever be a problem is if these were all zeros back here. And even then, we still round it up just because. If you got into mechanical engineering and mechanical design, there would be some other processes where you have to worry about tolerance buildups and error buildups and stuff like that. But we're not going to talk about that. If it's something you're interested in, ask me about it and I'll show you sometime. Okay, well, anyway, where does this come into the useful stuff, working with numbers? Let's take, for example, a number like 365. What we're used to seeing there is not a full number, the 3, 6, and 5. It's an abbreviation of the full number. The full number would look like this. When you were young, you might have called this expanded form. Oops, not tens, tens. It'd be 3 hundreds and 6 tens and 5 ones. And when we write it out that way, we can see that not only does the number have a count in the name, every digit has a count and a name. This is 6 tens, 5 ones, 3 hundreds. So let's add this to something. Let's add this to 232. We'll write that one out in long form as well. 2 hundreds plus 3 tens and 2 ones. When we were taught how to add numbers, it was stressed to us by our teachers that you had to make sure you lined up the columns, right? Well, why? Well, we just saw that when we add numbers, we can only combine things that have the same name. Since each digit here has a name, which is its place value, we have to line up those columns because we can only add tens to other tens, and ones to other ones, and hundreds to other hundreds. So we have to line them up in the columns so that we can combine the things that have the same name. Once we have that, we can just go ahead and add down the columns. 3 and 2 make 5 hundreds. 6 and 3 make 9 tens. 5 and 2 make 7 ones. Some of you might be looking at that right about now thinking, he did something wrong. What did I do? Did I catch it? I went backwards. I started on the left and I worked my way to the right. How have we been taught? How do we normally do addition and subtraction? Right to left. Why do we start in the right and go to the left? Yeah, exactly, in case we have to carry. Let's say I have 493 and we're going to add 287. We would normally start on the right and work our way back to the left because we run into this. 3 plus 7 is 10. Now we can't have two digits there, so what do? Keep the 0, carry the 1. 1 and 9, 10 plus 8, 18. Keep the 8, carry the 1. 1 and 4, 5 plus 2, 7. 780. Now believe it or not, that process of carrying is a relatively new one. Now, by new, I mean a couple hundred years old. Before that was developed, one of the possible ways that addition was done looked like this. 4 plus 2 is 6. 9 plus 8 is 17, so 7, drop the 1. 3 plus 7 is 10, so 0, drop the 1. Notice I get the same answer. I don't show you that in an effort to get you to change the way you add numbers. I only show you that because it's always been stressed to us that there's exactly one right way to do things in math. That's not true. I could show you 4 or 5 other ways to add numbers that work every time, but I'm not going to do it because I don't want to confuse you. But the point is, just because you don't do things my way does not mean you're doing them wrong. For subtraction, I'm not going to write these out in long form because I think you guys get the point now that you have to line them up because of the place values. So we're going to go ahead and subtract. 5 minus 2 is 3, 9 minus 3 is 6, and 8 minus 7 is 1. Again, what did I do? I went left to right. We're used to going right to left in case we have to not carry in subtraction, it's borrowing, yes. case we run into something like this. So starting on the right, working back to the left. 2 minus 9 can't be done, so what do? Borrow from the 5. This becomes a 4, and this is now 12. 12 minus 9, 3. 4 minus 6, can't do it, so we borrow from the 7. This is now a 6, and this is 14. 14 minus 6, 8. 6 minus 2 is 4. Once again, that's a relatively new process. One of the previous methods looked something like this. 7 minus 2 is 5. 5 minus 6 can't be done, so we're going to take from the 5. That's a 4. This is a 15. 15 minus 6 is 9. 2 minus 9 is a problem, so we take from the 9. It's an 8. This is now 12. 12 minus 9 is 3. Again, not trying to change what you do. My point is that there are different ways of doing things. And to be honest, I'm a realist. I realize that since you're allowed to use the calculator, you're probably going to. Now, I will tell you this. On the first test, the first 2 pages of the first test, you're not allowed to use the calculator. So just so you know that coming up. But anyway, for the most part, the calculator is there, and most people are going to use it when they're allowed to. But if you're like me, I have these fat fingers anyway that cause problems. But sometimes there are issues entering things in the calculator. For example, this 493 plus 287. It wouldn't be uncommon for me to go to enter this and do something like this. You get 520. Does that sound reasonable? Well, it might if you weren't paying attention. The calculator said it, so the calculator's always right, so you write it down and you go off life, right? What happened there? The 8 didn't register when I pressed it, did it? Obviously 520 isn't right. We got 780. And I did that by hand, so we know it's right, right? Another possibility that sometimes happens to me would look something like this. $3,300. Does that sound reasonable? Well, again, if you're not paying attention, it might. You might write it down and go on with life. The point I'm trying to make is if you're going to use the calculator, look at the problem before you start punching numbers in and develop some idea of what you expect it to be. If I'm looking at this, I'm thinking, okay, this is about 500. This is about 300. To estimate that, of course, these are both hundreds, so I can combine them. 5 and 3 make 8. And I'm going to keep the same name of hundreds. So I'm expecting my answer to be close to 800. Same for the subtraction. Down here. Well, this is close to 800. This is close to 300. 8 minus 3 is 5. I'm expecting an answer around 500. My calculator spits out 483. I'm comfortable that that's in the ballpark. So your multiplication quick. This one I am going to write out in long form, just so we can see where things come from. So we got 2 hundreds plus 3 tens plus 1 times 3 tens plus 2 ones. When we multiply, do we need the same name? No. So this 3 tens here not only can combine with the other 3 tens, but it can also combine with the 2 ones. In fact, every digit in this number can combine with every digit in the second number. And that's exactly what long multiplication is just an organized way of making sure every digit in one number gets combined with every digit in the other number. Of course, the way we do that is we usually start with the last digit of the bottom number, and we start at the end of the first number, multiplying them together. Just like we did a few minutes ago, we're going to multiply counts and also multiply the names. So 2 times 1 is 2. 1s times 1s is 1s. Then over to the 3 tens. 2 times 3 is 6. 1s times 10s is 10s. Anything times 1 is itself, right? Then times the 2 hundreds. 2 times 2 is 4. 1s times hundreds is hundreds. Now, before we can move over to the 3 tens, what do we have to do? Put in a 0. The reason for that 0 should become apparent here in just a second. It's So now I take the 3 tens and we go 3 tens times 1, 1. Well, what's 3 times 1? 3. Tens times 1s is tens. We had to have that 0 here so that our tens line up with each other. 3 tens times 3 tens. Well, 3 times 3 is 9. Tens times tens is hundreds. 3 tens times 2 hundreds. 3 times 2. 6 tens times hundreds is thousands. And now, of course, we just combine our columns. 2 and 0 is 2. 6 and 3 is 9. 4 and 9 is 13, so 3 carry the 1. So 7,392. Now, once again, I don't expect you doing a lot of long multiplication by hand, at least not after the first test. But again, if you're going to punch that in a calculator, I would look at this and say, okay, this is about 200. This is about 30. I'm expecting an answer around 6,000. Now, the 7,392 is a little bit bigger than that, but both of these numbers were rounded down, so I'd expect my estimate to be a little small. Okay, division. Division is the process in math that has been altered and changed the most. They've tried to simplify it because it is a little bit of a long process. And they've simplified it to the point where it's really tough to recognize what's going on. Like so many of our processes in math, it's just become a process we've memorized and have no idea why we do any of the things we do. Division's always been the one operation that goes left to right instead of right to left. Again, with no explanation as to why. So let's take a look as to why we do it that way. To do that, I want to take a little bit deeper look at multiplication because there is that deep connection between multiplication and division. If you go way back to first grade this time, when you were first learning how to multiply, before you memorized your multiplication facts and you knew that 5 times 3 had to be 15, how did you figure it out? Either count up by 5s or 5 plus 5 plus 5, right? We did repeated addition. In fact, that is the definition of multiplication, is repeated addition. Well, since division is just multiplication done in reverse, it then makes sense that division is repeated subtraction. So 24 divided by 8, if I subtract 8 once, it's 16. Subtract 8 a second time, it is 8. Subtract 8 again, it is 0. 24 divided by 8 is 3, because you can subtract 8 from 24 3 times. This also explains where our remainders come from. Let's say we have 24 divided by 5. Actually, I want to change this. Let's do 23 divided by 5. Just make it a little easier. So 23, subtract 5 is 18. That's once. Subtract another 5. 13, that's twice. Subtract it again. It's 8, that's 3 times. Can we subtract it again? Yep. Subtract another 5, we're at 3, that's 4 times. Can I subtract it again? No. So we can subtract 5 from 23 4 times with 3 left over. So 4 with a remainder of 3. So with that in mind, let's look at long division. Let's do something like 68,952 divided by 21. Well, we just said that division is repeated subtraction. I am not about to start subtracting 21 from 68,000. We don't have that kind of time. But if I could subtract it in big chunks, we could speed the process up. And that's exactly what long division is it's a process of subtracting large chunks of that number at a time to speed it up. How do we know how big of a chunk? Well, that's where the place values come in again. Now look at the number we're dividing here. This first digit, what is its place value? 10,000. So I'm going to take 10,000 times the number I'm dividing by. 10,000 times 21 is 210,000. Can I subtract that? No, that's too big, isn't it? That's more than what I have there. So let's go to the next place value, which would be 1,000. What's 1,000 times 21? 21,000. Can I subtract that? Yeah, in fact, I can do it A couple times. How many times can I subtract it? 3 times, right? 21,000 times 3 is 63,000. Leaving us with 5,952. But what I just did there, I subtracted a group of 1,021s, and I did it 3 times. So in other words, I did 1,000 times 3, or 3,021s. That process, I just subtracted 21 3,000 times. What's my next place value? 100. By the way, I'm never going to force you to do division this way. I'm going to use regular long division. I'm just trying to show you where it came from, just so you know. 100 times 21 is 2,100. Can I subtract that from what's left? You bet I can. More than once? Twice. That would be 4,200. Here's with 1,752. So there, what I just did, I've subtracted the 21 100 times 2, or 200 times. I just subtracted 200 21s. Next place value, 10. 10 times 21 is 210. Can I subtract that? You bet. How many times? 8. Perfect. 1,680. I subtract it. 72. So again, I just subtracted that 21 10 times 8, or 80 times. And of course, my last place value is just the ones. 1 times 21 is just 21. Didn't really have to do that. Can I subtract that from the 72? You bet, 3 times. Leaving with 9. So I just subtracted that 21 3 more times, telling me that I can subtract 21 from the 68,952 3,283 times with a remainder of 9. Now at some point we'll turn that 9 into a fraction or decimal, but for now we're okay leaving it a remainder. If we were to divide it out as a decimal, what does that come out to be? 2,283.428571423 approximately. Don't worry, it's not contagious. I do that just to prove a point. Math is about patterns. And one of the reasons why I take the time to show you the count and the name and that stuff, when you see numbers in that way, it's easier to see the patterns. If you can see the patterns going on in math, the calculations are easy. I could take this division out to probably about 50 decimal places before I'd start to get lost. But again, once you see the patterns, the calculations are pretty simple. Now you might be looking at what we did over here thinking, that looks absolutely nothing like what we were taught to do when we learned long division. And it really does look drastically different, but it is really exactly the same process. And let me show you how. The way we were taught to do this is you start with the 21. Does 21 go into 6? No. So we leave it blank above the 6. That's what we did here. We tried the 10,000. We got 210,000. It won't go in there. So we move to the next place value. Does 21 go into 68? Yeah, 3 times. Now, some of us were taught to do this. Others were just taught to do 3 times 21. But some of us were taught to do this. 21 times 3 is 63. And subtract to get 5. Well, what we just did there is exactly what we did over here. Take a peek. We got 3,000, 63,000, and the 5. Only over here, we just left out all the zeros. It is exactly the same process. The reasoning is exactly the same. It's just we shortened it up to make it fit in a smaller space and to save a little time. And somewhere along the line when they were teaching it to you, they forgot to tell you about all this. Anyway, once again, I'm not going to expect you guys to do a lot of long division by hand. To be honest, long division is the one operation I avoid doing by hand if I possibly can. But I do expect you to look at this and say, okay, we're looking at something around 60 or 70,000 divided by 20. 7 divided by 2 is between 3 and 4. You divide by the cancel out a 0 when you divide, so you got 3 zeros. So it's between 3,000 and 4,000. Okay, with that, I've run a little bit long, so let's take our break. It's 11:22, so let's come back at 11:32.